Here's ECET273 Modern Energy, lecture number 6. This is Mr. Pillar again, and we're going to continue with transformers. So again, more on chapter 5 from the Square 9 text and unit 3 from the Frodo Patrick text. We're going to go through and describe characteristics of three-phase transformers, configure 3 single-phase transformers to operate as three-phase bank, because you can purchase them either way. Input and output voltages, currents, phase voltages, and currents for each of the 3 phase transformer connections. Kind of give a look at what's going on there. So here are 2 of the types of 3-phase transformer setups, right? We have on top here, we have a delta-delta. So hardwired as though we have 3 single-phase transformers, H1, H2, X1, X2 would be one setup, and then so you have this transformer going across here, and here's how we would wire her up. We bring H1 in, H2 would be the other side, H4 would be one side. We bring H2 and H3 together, H4 and H5 together, take H1 and H6 together, and that creates our delta on one side. Again, on the secondary, we would follow that up with the same pattern. As you can see, they put them all in series and then pull off taps at the nodes. That's a delta-delta. On the bottom here, we have a delta Y. So the primary is a delta, the secondary is a Y. This is the kind that you would see, primary being the utility side, because remember, they don't need to bring in a neutral to us. Secondary being the customer side, with a delta, because we want to be able to have this point right here, this neutral. So here, the primary, we already discussed how delta sets up. The Y would set up with A leg, B leg, C leg, and then we bring in the low side of each of the 3 coils, tie them all together. That would be our neutral point, so you can tie on a neutral right there. So that would be the way we would arrange single-phase transformers to do a delta-delta or a delta-Y. Next we have a YY, okay? We already discussed how the Y would set up, but you have an input A, B, and C, and then between here on your low legs will be your neutral. A, B, and C, and here again is your neutral. There's your neutral point, there's your neutral point. I will use a caveat to say that a YY is not a desirable connection, and we're going to talk about that in a second. Then we have a Y delta. This would be more so inside of a facility. We would have a Y system coming in, going to a delta so that it can go to some kind of a 3-phase load. Most likely a motor, could be a heater, could be an oven of some kind. But again, same connection, A, B, C with a neutral. We have A, B, and C, all of these in series together. Different connections of the same transformers can yield different line voltages. So define the 2 voltages between the ratios as bank ratio and phase ratio. So what does this mean? Bank ratio would be the ratio of primary to secondary line-to-line voltages. Phase ratio would be the primary to secondary phase ratios. In the last lecture we talked about our turns ratio. Please note the phase ratio is equal to the turns ratio. So the phase ratio is equal to the actual number of turns on either side in ratio with each other. And like I said, that we were going to talk about YY connection, and has a disadvantage. What you end up with is if you have third harmonics, and we're going to talk about harmonics. We talked about them in power, the power, we talked about them in the problems that we have in the power grid. And the third harmonic adds up and it adds up on the neutral. Multiples of 3 on the harmonics of the FFT when we use nonlinear loads add up on the neutral. And if you have a YY system, you do not have a barrier between your neutral and primary and neutral and your secondary. So anywhere where there are those harmonics, you're going to get that damage and possible of damage on either side. You could solve it in two ways. You can solidly ground the primary and secondary neutrals together. Another way is called a tertiary coil, and we're going to do that in lab. Disadvantage is some load current actually ends up on the primary neutral, and then the harmonics interfere with adjacent communication circuits. Go across the board of all the problems you can imagine there. And I kind of wanted to show just another time here the way voltages could be broken out. On the left here, diagram A, we have secondary windings of a transformer set up in a delta configuration, and between those we have from A to B, from B to C, and from C to A we have 480 volts. So that would all be the same. Can we get another voltage? And the answer is yes. Off a delta, we use, like we had shown on the residential setup, we could do a center tap, and between them we would end up with a divide by 2 ratio, not a divide by radical 3 ratio, because it's actually it's a center tap and not a 3-phase voltage. We could also end up with a 208-120 setup here with the Y. So this is kind of showing all the differences between 3-phase voltages here on this Y, 3-phase voltages on the delta on the top, and we actually have single phase within a 3-phase system here on this delta on the bottom. Rated voltages for 3-phase transformers are line voltages. The ratio of the line currents is 1 over the bank ratio. Okay? That's usable for your bank ratio, and remember, your bank ratio is your line-to-line voltage ratio of primary over secondary. 3-phase power formulas apply, and so I put them up here again for you. The magnitude of your apparent power is equal to radical 3 times voltage line-to-line times I-line. Your apparent power 3-phase is simply 3 times your single phase apparent power. And then using Pythagorean theorem, we can find your P3 phase and your Q3 phase. Here I kind of want to show you, this is out of the photo text. This is figure 10-1 out of the photo text, and it shows a complete run up here at the top. It's a 13.8 kV alternator. That's a generator. This is actually a source that goes into a transformer. You can see the core here, primary, secondary, that steps up to line voltage. That line voltage then goes through to this transformer, this primary and secondary, and goes out to a substation. That steps all the way up to 34.5 kV. We head out of that and we go out to a secondary into a 4160 line. A 4160 line would be distribution in a neighborhood kind of a setup, down a city street, in an industrial park. So here we go to a 3-phase load and an industrial load. Here would be a commercial building and an apartment house, and then split off into other homes. I zoomed in on areas. This is the upper area of that first block. So there's your alternator, your transmission line, your 138 kV transmission line to a substation. Substation drops it down to 34.5 kV. That sends it down to a 4160 and then sends it into a commercial residential area. Here's the 3-phase load in a industrial setting. Continues on down that transmission line, taps off, goes to a commercial building. Imagine this to be just a small shop of some kind.
Here would be an apartment house. Now we split out with the center tap again. We have 120, 240 set up. 480, 240 up here. 480 would be needed for HVAC equipment. We could go to a farm like this. There's a lot of equipment on farms that need 480. Go ahead and go to lighting, whatnot. Inside this building, we would have a 240 to 120 or a 480 to 120 to distribute to low voltage. Here would be a distribution down the street. Usually 3-4 houses all share a transformer, depending on the load here. There's your split phase, center tapped, 240, 120 setup going into a house. But I kind of give you a visual of how we distribute power along the way. Let's do some math here. 3-phase bank built from 3 single-phase transformers. Each of them are rated 100 kV, 2400 to 120 volt. Find the line current on the primary side. Well, I want to set up the primary as a Y. I didn't define that, so we're going to do both Y and delta. The primary current on the Y, well, you would take your V phase is 2400 volts, which is V line to line. Which is V phase. Line to line is radical 3 higher than that, so there's your 4160. So if you take your each bank is 100 kVA, so 3 of them, your S3 phase is 300 kVA divided by radical 3 times your 4160. That's your line to line. You end up with an I line of 41.67 amps. Here we have a delta setup, 2400 volt line to line. Remember, your phase and your line voltages is the same value now. So you take your same 300 kVA divided by radical 3 times 2400, and you end up with 72.16 amps. So you have greater line current on the primary for a delta than you would on a Y. That's because of the radical 3 factor, the difference between your line to line and your line to phase set up in the neutral. So that's a way of looking at how you would build and find those line currents in a primary. Crosses over into the secondary on the same pattern. So summary, I gave you 3-phase transformers, multiple hookups. I gave you some calculations for line current, phase current, 3-phase apparent power. Thank you very much.